Okay, so we are introducing extra complexity into our logic, and that is the quantifiers right there in the preamble. So if you look at the top, well, first of all, remember that what we're talking about is the statement which is simply A is even. Okay, so if you prefer, this is what I'm looking at, this statement. Okay, and but it is made up of this statement simply at the top. A of x is even. Okay, so and then we can do so much with just one statement. And this is in the box we combined several statements made of still the same original statement. So we're saying that number. Well, how about I put x and y here? X and y. Okay, so we're saying one statement is x is even, and y is even. Two statements, already new statements, combine them together in the yet the new statement, ax and ay. Okay, so both of them are even. Then yet we extended it furthermore into with the two quantifiers in the beginning. We're saying for any x and any y, if well, I guess I might need parentheses here to make sure that we understand the logic. So okay, let me start over. So we have two statements: x is even, y is even. Combined together, yet in new statements, x and y is even. So that's what on the left-hand side is this one. Okay, and then on the right, I have a statement which says that x plus y is even. Okay, and then I get bigger statement. I say that if x and y are even, then x plus y is even. Okay, but it is the question. This statement remains incomplete if we don't put the preamble there, and that to introduce the variables there. So x and y are the variables of our statements, and the truth of those statements depend on x. Okay, so then I have to introduce them appropriately to say either I'm saying that they're always true or they are sometimes true. So this is a statement that we started with well, in the very beginning last week. And so if so for any x and y integers, if both of them are even, then their sum is even. That's all there is here. So this is a decomposition of this fairly simple statements that we've made about algebra. Now it is written in a more logical way, and there is really nothing. I don't want you to think that there is something absolutely unavoidable here. So there is really nothing wrong with it. If you look at just about any book, the language that is being used is the language of whether it's plain English. Okay, that's what we have on the right. Sometimes they be more careful about writing if and then, or for any and for all, but the symbolism is not as actually commonly used in any kind of in any kind of text. Okay, so certainly I don't think you've seen anything like this in a calculus textbook, right? So because it's certainly doesn't make things easier. It looks very foreign, and you kind of distance yourself from the subject matter. But that's what logic is. So it is something that is sort of above the on top, you put on top of, or you use it, I don't know, as a microscope to study something, but you can use this microscope to study this or that, and it equally applicable. So that's, in other words, it's just a tool, means to an end, and we just have to be careful, learn how to use it to our advantage. And one of the things is whenever if you're talking about something like numbers being even, it is fairly straightforward, and you know what you're talking about from the beginning, and that's the point. And we'll try to stick to that as much as possible with this course. But if you go back to calculus, some of the statements are pretty complicated, and such as this. This is L is limit, and as you can see, the definition is a little bit complicated. And so what do you do with it is, for example, how do you prove it? How do you disprove it? Logic will help a lot with things that are hard to understand to begin with. Okay, so we'll get to that, but let's examine a few more statements. So here I try to say any number. Where is it? Well, here it is. Over here, there are even numbers. So I'm using the other quantifier, which is translated as there is. So this is the little dictionary that we have created. This symbol for any, and then there's a symbol there is. It is, like I said, in every book you might never see those symbols, but you definitely see the logic. So you'll see for any, you see there is, even though as I try to write it here, the wording might be very different. So for any, for each, for all, and instead of there is, there might be there exists, and sometimes, and that's either for better or for worse, sometimes the quantifiers, when written in plain language, they don't appear in the beginning, but they sometimes appear at the end. Okay, so for example, well, you say that language like that, x plus y is even for all even xy. See how it's exactly the same statement, but it looks it is like the grammar is turned upside down. So English, there's nothing wrong with the English, but if you want to put it in logical form, then you put once again these quantifiers goes in front of the statement, whether it is a symbols or just a plain language. There is. Okay, so once again, at the limit, we'll take a careful look at the, or as an example, the statement of definition of the limit, just to demonstrate the power of the logic. Power of the logic that allows you to not to think about it. So some logic is in many ways is like algebra, and you can actually compute things without understanding what they mean. So it's an advantage. About a half here, but you need practice, and you don't want to really rely on that too much. So I want, as for practice, I just have here, I found something. Where is it? On. Oh, here it is. Yeah. A few days ago, I found this on Facebook, of all places. Okay, gonna open or not? It's so stupid. Okay, let me start over. We don't need this. Just open. Open with. Open with. Paint. Okay, so. Okay, so just read the statement first, and then we'll practice with this logic a little bit. Okay, so bxy, just the same way we just talked about. So it's a statement with two parameters. So instead of numbers, we're talking about persons. So person x, that's a statement, as you can see. So let me highlight it maybe. Highlight. Where's highlighter? It's a highlighter. Okay, well. This is so in quotation marks. Person X accidentally bumped into person Y on the train. Okay, so then we have a bunch of possibilities. So you can imagine that there are two parameters, and each of them can be either accompanied by one, the quantifier, or the other. So as you can see, there's a bunch of possibilities, and then in a random order they translate into plain language on the right. So you have to match up the statements on the left, logical statements, and statements on the right, which is in plain language and kind of written in a informal way. Okay, so let's. So is it clear what we're trying to accomplish? Well, let's do one. So can you, let's take a look at the first one. So this one. Okay, so can anybody read it, what it says? Just don't try to translate, just say what it means. Translate into plain language, and then we'll find a match for it.
There exists an X and there exists a Y?
No, in terms of the description at the top.
like there is a person accidentally bumped into a person while on the train.
Yes, in other words, there are two people who bumped into each other. That's
Right.
it. So there's a guarantee, or there's only one accident. Let me see. Which one do you think it is? It is correct.
For the one you circled?
Yes.
The third one?
That's right. Unfortunately, it happens. I think so. So unfortunately, it happens. So when there is and there is, it means that there's only one incident that we can be sure to talk about. So maybe it happens more often. We don't know. The statement is we take it as the only information that we have is that it has happened. Okay. So and then what do you say? You say unfortunately it happened. So that's the link. Okay. So that's the translation over here. Okay. Okay, so let's try the next one.
What is the notation for the upside down A again? I can't remember.
For any.
For any, yes.
Okay.
So there is, and for any. Okay, so once again, a little by little does have to happen simultaneously. So the second statement.
Maybe the second one down?
Yes. Yeah, on the left. So once again, we're translating it from the logic into English. Just read it out loud.
There is a person X such that there's a person Y.
There's the second symbol. Look at the second symbol.
Oh, for any Y. Oh,
Yeah.
There is a person X for any Y. I don't know.
Can you explain what is that we're saying?
I would guess. I think that's.
Somebody's bumping into
Yeah.
everyone? One
No, the other way around. One person being bumped into.
Someone's always being bumped into. So
Look at the original statement. X
Oh,
is
you're
bumped
right.
into by Y. So some person
Yeah.
has been bumped into by every single person on the train. So I don't know which one.
I guess it'd be.
I think it's the second one. Maybe somebody was blocked. No, no, that's one person. That we'll get to that. No. Well, hold on. Where is it?
So if
It's
there's
like-
one person who keeps on hitting.
Somebody. No.
Yeah, is it one person?
Okay, and everybody bumped into him. That's right. This is the one. So if that person was blocking the exit, everybody bumped into him eventually.
Okay, there's one person.
Okay. Okay, let's try go the other way, which is just as interesting. So how about let's take this one. I think we can handle this one.
Yeah.
Super klutz runs through a train. So it's kind of the opposite of what we just considered, right? So can you logically translate it? So one was standing at the exit, and everybody was bumping into him. This one is running through the train and doing what? Bumping into everybody. So what is it?
The reversal.
The reversal. Which one is it?
The next one.
Yeah.
The third one, right? Yeah. Okay. So there isn't a lot left. Okay. Universal suffering.
Is that just out the next one for any X's? I mean, everyone's hitting everyone.
Everybody hitting everybody. I think so. Yeah. So this one. Everybody universal suffering.
I want my money back for that train.
Okay. Extreme. Okay. Well, let's look at the logic. So the next one on left. So there is a person Y. See, they flipped the order of X and Y. That matters. X is not the same as Y. If you look at the statement B, X and Y are not interchangeable. Okay. So if we now let's try to understand what the next to last statement is saying. What we're saying if we're stating it. So there is a person Y which. What did he do? Hold on a second.
There's a person operating it, so...
Every single person.
No, there is one person. Hold on a second.
So I think
What is that? Somebody was blocking the exit. Did we do it right? No, we didn't do the blue one. Isn't right. This is the blue one. The Y is the superklutz. Okay, so sorry about that, but this is simply not correct. Do you see what I'm saying?
Well, what's the difference between a chaos train and the super klutz running through the train? Like, and
Well, because there's only one klutz.
okay, so what's the difference between chaos train and universal suffering? Because that's everyone hitting everyone. I feel like a chaos train would be everyone hitting everyone.
Right. Well, let me first finish this correction. So you see that this statement. Come on. These two match, right?
Okay.
So there is a super klutz. Klutz is the one who bumped into somebody, not vice versa. Right? So that super klutz runs through the train, and so one klutz, so the super klutz, there is a super klutz. What does it mean that he is super klutz? That he bumps into people, and he runs through the whole train, and that's why for any X on the train, that X has been bumped into by the same person. Okay? So let's now take a look at the one that we skipped. So for any X, there is a Y. It means that nobody is. Well, let's understand what that statement in the middle means. So for any X, every person being bumped into by somebody, but we don't know who.
Okay.
It is not necessarily the same person.
Yeah, yeah.
So
The first.
Yeah, that would be,
Chaos train?
yeah, chaos, yeah.
I thought,
Or it could be
I thought Y was getting bumped into by X.
yes,
That
yes.
says there exists a Y, so.
There is a Y. So if I'm a person on the train, then and any person on the train has been bumped into.
But X is
by
doing the
somebody.
bumping, right? And
Yes.
Klutz-
No, X. No, but Y bumps. Person X. Oh, I'm sorry. Shoot. I messed it up. I thought there was an is here. Is actually. But. Okay, so that changes everything.
So was our original answer right? Because there's only one X.
I don't see any other way just to start over. I'm sorry. Okay. Can you close it? Don't save. Okay, sorry about that. Stupid thing. Open with. Paint. Okay, same statement. Okay, starting over. Let me. So X is the perpetrator. X is the bad one. Okay, so we're going to bump into person Y on the train. So X. Okay, I don't know. This is X, and this is, so the Y is the innocent bystander. So X is running into Y. Okay, so this symbolism might help. And this is Y. Okay? So X running into Y. Okay, starting over. So the first one doesn't change, right? So there are two people who bumped into each other. Okay, so that's okay. We are fine with this, right? Two persons bumped each other. Unfortunately, it happens. So there is no difference here. Okay? So now there is somebody runs into everybody. Okay, that's a klutz, right? That's the pretty bad deal. So X is the klutz running into every single person. Super klutz right there. Okay? So now if we flip what we're saying that, well, now that's what the third statement, what does it say?
That's gotta be somebody who's blocking the exit.
Right. Yeah. So, poor guy. Well, it's his fault anyway. Right? Don't block the exit, otherwise everybody will bump into you, right? That's what it says. Okay. Okay, so now chaos train or universal suffering. That is the judgment call. So let's maybe go to
Should be extremely crowded.
That just says when there's a
extremely
person.
crowded. Yes, but it doesn't mean that it is crowded here, crowded there. It doesn't mean that this person will bump into that person necessarily. It's still crowded, right?
It's
So
just saying there's a random person bumping, so someone's getting bumped. That's random.
do you mean the state 4-4 statement?
Yeah.
Everybody bumps into everybody,
chaos train.
including yourself, by the way,
Okay.
which is really insane.
Oh, I'd say
Sounds
more
like
empty
universal.
train though.
It sounds kind of universal. So the list that seems to be better.
So wouldn't universal suffering be the next one? Because like you have, there is a Y who's hitting by for any X. So like that Y is being hit by every.
That's not universal, though.
But
Not
what if
everybody's
you,
getting
like,
hit.
Yeah. So
Don't both
super
people suffer
klutz,
when they get bumped?
running, bump to each other, and this is there's a person that been. Hold on a second. Isn't this? Hold on, I'm getting confused myself. Okay, so let's look at the bottom. Let's look at the bottom. So every Y there is an X. So so Y is the innocent bystander, X is the perpetrator. So the last statement on the left says that everybody has been bumped into by somebody else. That's all. So I think it is universal suffering because why? Because that's a suffering. If you bumped into, you suffer. And everybody, universal means everybody suffers. I think. That's my judgment call.
I would only argue, like I said, I mean, even though you're doing the bumping, it's still going to hurt you too, so.
That's fair. But, right, yeah, it still works. But the point being then, as you can see here, not everybody is doing bumping necessarily. That's the last statement. So it could be just as well still one person bumping into everybody.
Yeah.
So there are some innocent people there on the train, but everybody suffers.
Okay.
So I think this is a fairly good judgment. We have still two left, and so what is the difference? The one is that number 4 seems to be so obvious when so everybody's bumped to everybody. I think it is chaos train. Extremely crowded or empty train. So the possibility that the train is empty certainly should be kept in mind. But you see, by the way, how do we exclude the possibility with the rest of the statements? How do we exclude the possibility that the train is empty before we move on? You see what guarantees that it's not empty?
It says they exist.
There exists, but it has to be in the beginning. So, for example, the first one, definitely not empty because there was a collision of two persons, and so it was not empty. The second one also, the train is not empty, but the last one could be empty. The last one could be empty. So every person on the train has been bumped into, but maybe there are no people on the train. So it's still okay. So this could be empty. This is not empty.
So could that be empty? 4 down, could that be empty?
This one, yeah, it could be.
For any X?
But we have in both cases we have the possibility that it is empty. So we have to use judgment and say chaos train or extremely crowded train.
what's the difference between those though? Like, you have an
I'm not
extreme-
sure.
Yeah.
Well, so let's look. That's good because that makes sense then to start on the left and actually look at the logic and see the difference. To understand the logic is the point. So that one, the fourth down, seems the most obvious, and it is really. But so it's definitely worse than the last one, the second from the bottom, right? The second from the bottom says, what does it say? It says that.
There's a Y for any X, is that what you said?
No, there is no, not for any X in the right order. There is one right person that's been bumped into by every X. I thought we already had that.
No.
No, somebody blocking the exit. Oh, no, that was wrong. This is the blue one. This is the blue one. Okay, so, with another mistake.
For any
So once again, that indicates certainly the how careful we have to be about the logic. So there is a person to begin with. So for any X there is a Y. That's not the same. It means that everybody has been bumped into. So that's a bad idea. That's number 3. But there is one class that there is. If it starts with there is, that's the problem. So this is. Okay, so this is the one. Okay, so once again, let's try to read it. Yeah, there is a Y. Somebody who has been bumped into by every single person on the train. Why? Because he was blocking the only exit. Okay, so number 3. Number 3. What is so bad at that? Hold on. Do we have a? Okay. Number 3, then every person bumped into somebody. That's number 3. right? Everybody X is the one who bumps into people, and he has bumped to, so every person bumped into somebody. Okay, so but it does that's chaos, but it's not universal suffering because some people may have not been bumped into, right? Right? Number 3. 1, 2, 3, 4, 5, 6. So for any X, there is a Y. For any X,
So the third one should be the last one, right? Because it's for any X, there is a Y, so it means it's crowded, because for each person X.
what I'm saying is that number 3 is not universal suffering. Okay, well, that's not the question. The question is, of those remaining 2, which one is it, chaos or extremely crowded?
Are you saying there's people not getting bumped into on number 3, possibly because
Possibly,
you have
yes.
10 X's and you have 20 Y's? I mean,
So
you
that's right.
satisfied the 10 out of 10, but
Yeah.
you got 10 Y's not getting bumped.
Yeah, so
Okay.
I don't know how to characterize it. Certainly, in number 4, everybody has been bumped into. So I'd like to say that number 4 is chaos. So chaos, like you imagine chaotic motion of say, gas particles. They run all the way around and bumping into each other all the time. So everybody has a chance of bumping everybody, and that's I think what it is. And number 3 is, like I said, it's just extremely crowded. It is extremely crowded because so everybody is within a crowd, surrounded, and that's why it's been bumped into. So if you're in a crowded train, you're likely to be bumped into at least once. So that's what it's saying, I think, right?
To me, 3 almost sounds like it could be unfortunately it happens, because saying like for any perpetrator there is a victim. So, like,
No, for any perpetrator, there is a victim. Yeah.
Same,
Well,
would it be the other way around then?
what?
For every, well, no, never mind.
So unfortunately, it happens, but it happens to.
It's not saying it exists for sure, so it's not.
Unfortunately, it happens. It's kind of a. I think it is like about one individual incident here we are talking about. If it happened to everybody, then it is not. You don't say it just. Unfortunately, it happens because you have to say it to every single person. Okay, every person on the train, being bumped to it, and then you tell them that, well, unfortunately, it happens, but that it is really not. You don't feel any better because of that. Because
So that statement, there's a chance that there's no bumping, right? Because it's just saying for any X.
if unless it's empty, the whole thing is empty. Otherwise, no. Number 3 is every person on the train, if there is any, has been bumped into. So that's why I think it is crowded. Okay, this one. Extremely crowded. So once again, my logic is that if it is extremely crowded, every crowded means that everybody is crowded around, and one of the people who surround you will bump into you. Okay. In the meantime, this is chaos. This is really chaos. Of course, it could be empty. Okay. So the statements on left are only they are informal. They match only so, but the point was you cannot match unless you really understand the statement on the left. So that was the point of the exercise. Okay, so so that's an exercise, and translating logic into plain language and vice versa. We tried both. Is a big deal, a big part of this course, and that's kind of skill that you acquire through experience, and it will be one of the so something to be expected from you on the test. You can actually look at there's a simple test from a couple of years ago. So it's not dissimilar from this. Well, dissimilar is what is make it informal is the statements are somewhat informal, and there is a room for different interpretations. So That's the thing about mathematics, then you state everything, and even in plain language, you still state it in such a way that there is no way to misinterpret it. So if you have some statement in mathematics and you have trouble to translating it into logic from right to left, it means that the statement is not entirely specific enough. Yeah.
Will this be in the notes that we can like go back and look at?
I could. Well, I mean, there's a video, right? But
Oh, okay, yeah.
I could certainly save it with the.
Okay.
I could do this if I just take this and copy and maybe paste. A little bit tiny. Why is it so tiny? No, that doesn't help. Okay, so if you can read it,
We can zoom in.
yeah, you can almost read it. Okay, so all right. So especially when you actually take these and rearrange them, I think it is much more convincing than these arrows that are just seems to be kind of random. And you can probably find it. That's where I got it from. But it was actually a video, and the video I didn't really watch. But there is another explanation somewhere online if you can find it. Okay, so all right. So what else we want to do with these? It is the big deal that we talked about several times is negation and how to negate statements. One thing that we already have considered is how to negate. Well, actually, we haven't considered how to negate implications. And it is tempting to try to reverse the arrow, and it's not the way it works. But you reverse arrows when you do either contrapositive or you do converse. But in general, it is simply not the case. Fortunately, when we only concentrate on suppose there is no implication, and we're looking at a statement very simple like that one, there are even numbers, or there is an even number. So it's the same thing. Then it's very simple to negate. Okay, so let me try it. So once again, so Ax is x is even. Okay, so what is the negative of x? Ax.
X is not even.
X is not even. Yes, that's fine. Yeah. And then what I'm trying to consider then, so we negated this statement. What if the statement is actually bigger, and it is slightly bigger? Well, the one that I considered was there is an even number. Okay, so that's my statement. Let's say B. Now this way, as you can see, A depends on X. B does not depend on X anymore because there is there. So the statement is once again there is an even number. Okay, so that's what it says. So what's the negative of B?
There isn't an even number.
Fair enough. So there isn't an even number. But can you write it in terms of in terms of A? So that statement on the right is fine, but if I want to express it in terms of the original statement A.
Write it with the A with the X with the bar over it.
There's a bar, so that's a negation. Okay, so I put it here, and then
There is X.
there is X?
I was going to put the same symbol, just
Yeah, I
drop
was
that
gonna
out.
say there exists an X such that A is not even.
That's not the same. There aren't any even numbers, and you were saying there is a not even number. It's not the same.
Oh, okay.
Okay, so what did I put there? No, there is an answer right there. We just talked about it.
For any?
For any, right. Okay, so that's the trick. So you flip the quantifier. There is uneven number or any number is not even. Okay, that's the negation. Okay, so let's try another example of this kind, how once again you flip how there is turns into for any if you do negation of statements. You can certainly once again go back to where's that thing? To this statement. Well, yeah, that's a bit too complicated. That's a bit too complicated. So let's pick a statement A of X. Well, once again, X is a math major. Say X is a math major. Okay, so it's very easy to say what the negative X is not a math major, right? But so that's negation is very easy to write if it's or might be if it is very simple plain statement. When there are quantifiers such as there is a for any, that becomes complicated. So once again, there is an X such that AX. What I'm saying here, statement B, what does it say?
There exists a student that is a math major?
Yeah, say maybe in this room, so there is at least one math major in this room, for example. That could be what we're saying here. And now if I want to negate it, to say that there is one math major in this room, what's the opposite of this?
There's none.
4.
There is none, right? But once again, if we want to put it in the standard form, the preamble with one or more quantifiers followed by the statement, which should be in terms of the original statement A.
For any student, there's one that's not a math major.
No, for any student that is not a math major. Okay.
Gotcha.
So if you saying something specific, there is something about a specific person. Well, not specific person. There is at least one of them. So what is the universe of the rest of the possibilities? It is either you check out every person and you discover that at least one of them turned out to be a math major, or you examine every person in the room and discover that none of them is. Okay, so this is the statement. So if there is during your investigation, either you discover that you discover a math major that's here, or you discover there are none, which means that every one of them is not a math major. Okay, so that's the second. Okay, so let's try a different statement. So let me. How about statement A? Something. Okay, X is positive. That's the statement. Okay, then I could once again. Well, certainly the X. I don't want algebra. Sorry, let's put something once again. About what a pen is red. Okay, that's it. So pen. There's a pen and it is red pen. Okay, so then the negative is naturally X is not red. So these are pens. Okay, but then now the statement that I might make is, say, statement C. There is a red pen. Okay, there is a red pen, right? That's what I'm saying here. So what's the negative? Suppose I have a bunch of pens lying here, and one of them is red. Okay?
And there's one that's not red.
What?
Would the negative be for any pin there is not one that's red?
That's right. Any X, not AX. So I go through all of these, and all of them are not red. Okay, so I'm checking one by one. All of them check them out, and none of them is red. So that's the second statement. The negation of there is a red pen. Okay, so as you can see, that the rule is actually very simple. You flip the quantifier. So from there is, it turns to for any, and for any into there is, whenever you do a negation. Okay? Okay, so so once again, it is especially applicable when there are more than one parameter, such as over here. Once again, back to the train. There are two parameters and two quantifiers. And once again, you could, turns out, that if you have two quantifiers, you, once again, to negate something, you would have to flip both of them. Okay, so for example, if I look at the green one, so unfortunately it happens, which says that there is, at least on that train, at least there was one bump happening. Okay, the negative is, what's the negative? There has been no bump. Okay, so can you have a negative of this?
For any
Negative.
X, there's no y, negative y.
No, for any. Once again, you flip both of them. Both of them, there is, and there is. Flip them for both to for any, and then negate the statement itself. Okay, so that's how roughly it works, and it is purely computational. There is that simple rule: how do you negate? You flip the quantifiers and negate the statement that follows. So the preamble is to flip, and then flip the statement itself, and then you can just sit back and examine and confirm that this new statement that we have produced indeed indicates what you want to indicate. And let's once again forget about everything that there is. The rest of the statements. Look at that one. And what to say for any x and for any y. So pick two persons on the train. What are we saying about those two persons on the train?
They're not bumping.
They are not bumping into each other. So any pair of persons on the train, we examine them, and there is no bumping. So which means that there is no bumping whatsoever. Okay. So we demonstrated that that statement about unfortunately happens is wrong, because it does happen, or at least it didn't happen this time. Okay, so you can do it in a similar way. Let's flip one. Somebody was blocking the only exit. Okay, so that certainly is a very informal way to put it, but let's do it anyway. So I want to negate this negative, opposite, whichever language you prefer. But it should cover all the possibilities in the world outside of this one. So what we're saying here is there's a person who may have been standing at the exit, and everybody bumped into him. Okay, so that's what we're saying. What is the opposite? Well, let's once again ignore try to figure out what's happening. Let's just do algebra. So let me write algebra. Therefore, any y, there is an x, bxy, negative. Okay, so now you can start from scratch, from this algebra. You can just start from scratch and see if it makes sense. So let's read this new statement. What does it say? For any y, so any person on the train, what can we say about him?
There's someone bumping.
No. There is somebody who did not bump into that person.
For any y.
There is an X.
There is an x, one,
Oh,
another.
yeah, the bar statement, yeah.
And then negative, right?
Yeah.
So for every person on the train, there is at least one other person on the train who didn't bump into him.
Yeah.
Okay, so that is the negative of somebody was blocking the only exit. So nobody was blocking the exit, and at least somebody was not bumped
So
into.
for the negative statements, you just flip what the statement is, like, I mean.
Right.
it's-
I flip the quantifiers to the opposite.
Quantifiers, yeah, that's
Okay,
it, yeah.
and then I negate the statement.
Okay. Okay.
Okay, so so that's a good example certainly, but let's still use it to something much more challenging, and that is the definition of the limit. Okay, from calculus 1, really a challenge, and even if you understand what it is, and do you remember facing the definition, epsilon delta? So was it a challenge? Am I right here? To understand what's going on? Well, did you get to prove anything that function is a limit, say, say, x squared, limit of x squared is equal to 0 as x approaching 0. Does this look familiar? Okay, so that's fine, but that's not, I don't want to really go into that, but what I want to do is, what if the question becomes, we want the opposite? What is the point of studying limits if they always exist? What if there is no limit? So how do you say that, a different way? So how do you say that limit of x squared, x goes to 0, is not equal to 0? How? Well, you negate. You take that statement, this statement, and you negate it. So L is the limit. Say, well, in this particular case, 0 is the limit. So 0 is the limit of x squared as x approaches 0. Okay, now I negate it. So that's my statement. I negate it, but then so 0 is not the limit. Okay, so that's fairly simple. But now we got to negate that statement over there. Okay, so the statement says for any epsilon there is a delta such that this is satisfied. Okay, so how would you negate it? What happened? Okay. Now how do you negate it? The definition right there.
When you say 0 is not the limit of x squared.
I already did. I already did that last line. A is 0 is not the limit. I want to now go to the definition and write it out. This is when it is a limit. This is the statement. Now I want the negative of it. So negation. How do I start? Instead of for any epsilon, what do I say? There is an epsilon. I keep doing this. There is an epsilon greater than 0. Then what?
For any.
Such that for any. Sometimes for grammar purposes you have to insert things. For any delta. Greater than 0. And then we can just say that this last statement is not satisfied, which is I'll just, since we are pretty much out of time, let me just write it like this. So this does not imply that f of x minus L is less than epsilon. So the requirement of the limit is not satisfied, but the preamble, those two quantifiers have been flipped. And now we have the negative. The statement all that remains is just to figure out what the bottom means. Okay, so I think I'll assign the first homework tomorrow. Okay.
You said tomorrow?
Yes.